See anyone. So I'm just going to be talking to my screen, but feel free if there are questions that the organizers can stop me. But today I'm going to be presenting some work that I've been doing in collaboration with my colleague Colin Phillips, who's at Utah State University, and with my PhD student Robert Kostanek. And so, okay. So today I'm going to be talking about alluvial rivers. So alluvial rivers are rivers whose containers are made up of the sediment that they transport through them. And these rivers have two main jobs, which are to move water and sediment across our landscapes. And the shape of these rivers is some expression of the river's ability to do those jobs of moving water and sediment. And in particular, alluvial rivers will evolve their shape such that when the river is full or at its bankfull condition, the shear stress acting along the bed of the river will just exceed what's required to transport sediment. And so if we look at many rivers of many sizes, both across the lab and the field, we see this remarkable scaling between bankfull width and bankfull discharge. And that scaling is well described by this underlying constraint that the rivers do evolve to exert that fluid shear stress on the bed that's very, very close to that threshold for particle motion when the river is at a bankfull condition. And there we go. It's worth emphasizing here that this model and this relationship only describes the stable bankfull condition. We're only thinking about discharge of one flood, which corresponds to that bank-to-bank river width at an individual cross-section in our river. But we know that our river experiences many flows of many sizes around that bankfull condition. And so this bankfull width is just a reflection of some average self-organized condition or average discharge. And so again, it's worth emphasizing that that bankfull geometry at our cross-section is strongly reflecting the threshold for motion of grains that make up the riverbed. And we can, in simple terms, represent that onset of motion of our sediment grains as the point where the driving stresses acting on our grain exceed the bed resistance. And so we typically call that this threshold a critical shear stress, or we can non-dimensionalize this quantity by our grain size and call it a critical shield stress. When we're thinking about that non-dimensionalized quantity, we have a tau star C. When we're thinking about dimensional quantities, we have tau sub C. And so this idea is highlighted really well by this video of a bowling ball sitting at the bottom of a flume. So you can see that the water is pushing against the bowling ball, applying some force that's driving that bowling ball downstream. But the bowling ball also has some weight, and it's only when those driving forces pushing the bowling ball overcome the resistance of that bowling ball sitting in place that that bowling ball starts to move. We can watch that again just to really drive the point home. There it goes. Okay. And so if we take this idea and then return to bankfull width, we can pick any data point on this plot and think about it as a single river cross-section. We can zoom in on that cross-section and we can map the shear stress acting on the bed when our river is at our bankfull condition. In the center of the channel, the water is deep enough that the shear stress is exerted that exceeds that threshold for motion, allowing sediment to move through that cross-section. But as we move towards our banks and our water depths become shallower, our bed shear stress drops below critical, such that our river can't erode near our banks and it can't widen beyond this stable bankfull width. And so we generally assume here, when we think about this threshold underpinning our width discharge scaling, that our threshold for motion is constant. And this is a fairly common assumption across fluvial geomorphology, both when we think about sediment transport models, but also morphodynamic models. And so we generally assume this, but multiple studies have demonstrated that the threshold for motion is not constant. Instead, Grain scale erosion thresholds can vary both in space and in time. And for a lot of reasons too. And so first, empirical studies have demonstrated that the threshold for motion can vary with reach scale differences in channel slope, such that as we get to steeper slopes, the threshold for motion increases or requires a larger flow to dislodge and transport sediment particles. A number of studies have also demonstrated that the threshold for motion increases with bank cohesion. This isn't that surprising that it's harder to move stickier sediment. And then Dunn and Gerald-Mack also demonstrated that for sandbed rivers that have cohesive banks, that the shear stress exerted on the bed at that bankfull condition is reflective of this threshold for motion of our more resistant sticky material. So there's this relationship again with the mobility of sediments that make up our river and our bankfull width. And then there's also been a really long legacy of scientific inquiry devoted to the effects of grain scale topography on the threshold for motion. So this includes accounting for differences in grain protrusion, differences in grain shape, and patch scale dynamics, or differences in grain scale topography at these smaller patch scales. And so one example of this is that as grain protrusion decreases, particles become more shielded from the flow, and thus our threshold for motion increases. Threshold for motion can also increase with decreasing sediment supply. So as we decrease our sediment supply here, our bed becomes more armored, our grains become more interlocked, and thus become more challenging to move. Recent research has also demonstrated that these differences in sediment supply can lead to measurable differences in channel aspect ratio, such that as we increase our sediment supply, a river cross-section will become shallower and wider. And that decrease is suggestive of that widening is suggestive of a decrease in the threshold for motion with increasing sediment supply. And then finally, a problem that I've spent much of my career so far thinking about is this observation that the threshold for motion can vary with flow history. So first, there have been consistent observations that as we decrease our flood frequency or increase the time between our storm events, the threshold for motion for the next event will increase, such that for the same flood stage discharge, less sediment will be transported. So Reed et al. First noted this effect in the field, observing that the threshold for motion in a gravel bed stream increased with that increasing time between storm events. And then I carried out some experiments as part of my thesis work, which demonstrated a similar effect, such that as we increased the time between floods, the total bed load moved during the subsequent flood decreased. Again, implying this increase in bed resistance or in the threshold for motion. When we're thinking about flow history, we can also think about how the threshold for motion evolves with changing flood magnitude. And so we interrogated this idea using 19 years of critical shear stress measurements from the Erlenbach, which is a mountain stream in Switzerland. And the data set we used for this was incredibly unique because this channel is one of the most well-monitored streams in the world. There are over 3 decades of continuous bedload transport measurements that have been made here. There are geophones that are installed in the riverbed that can measure the individual impacts of bedload particles as they bounce by. We can use those impacts to identify the threshold for motion for individual transport events, and we did this using a 19-year record of over 500 individual events. And so what I'm going to show you today is how the threshold for motion for any flood event, denoted by this pink star here, and which is plotted on this y-axis here, changes or evolves as a function of the shear stress at the peak of the prior flood event, which is what we're plotting on this x-axis, what is denoted by this teal triangle. And so first we'll look at small to intermediate sized floods. And what we find is that with increasing flow magnitude, we see an increase in the threshold for motion for the next event. All of these events tend to be below the bankfull condition at the Erlenbach. And we hypothesized that during these events, there's a local rearrangement of riverbed sediments that ultimately acts to stabilize the bed by reducing protrusion of grains, pivoting precariously placed grains into pockets, and ultimately increasing bed resistance and thus the flood size required to mobilize sediment for the next event. And so if we look at a picture of the river during an event like this, we can see that most of the channels submerged in water, making it likely that we do have enough power to do that local reworking that's necessary to strengthen the bed. Now, we can also look, if my slides will let me advance, we can now look at our highest discharge events that the Erlenbach sees. During these events, we always see sediment transport in the river. Often these events exceed the bankfull condition. And for these largest flows, the threshold for motion becomes independent of our prior flow events. And we can see that for our most extreme events here, the threshold for motion decreases significantly and the bed seems to be reset to its weakest state. And so this is a picture of what the river looks like during one of these highest flows. And as you can see, it's pretty extreme. And flows like this have the ability to move boulders, they can cause landslides, and they can effectively disrupt the bed in a whole bunch of different ways. So it's no surprise that these events have the capacity to weaken the riverbed through those processes. And so from our observations, we can start to describe this evolution of the threshold for motion as this competition between these strengthening and weakening effects. And these can change both with changing flow magnitude, but also with changing flow frequency. And so it's that flow history effect that leads to these integrated shifts in the threshold for motion with time. Okay, and so I motivated this talk by telling you there's this strong coupling between the threshold for motion of the particles that comprise our riverbeds and the shape of our river, so specifically the channel width. And now I've just told you that the threshold for motion can vary in space, it can vary in time, it can vary in response to a number of different drivers. And so now the question is, what are the impacts of that variability in the threshold for motion on bankfull river width? And so we can, for example, here, we can choose a constant discharge or a constant condition on our scaling plot here. And we find that there's over an order of magnitude and variability in channel width for that given bankfull discharge. And so we can think about that as if we're sitting below the central tendency of this data cloud, we're deeper and narrower than our average for this flow condition. And if we're sitting up here, we're wider and shallower than average for our flow condition. And so what we're interested in interrogating here is saying, can we attribute these differences that we observe for a constant bankfull discharge to variable erosion thresholds at the scale of individual river reaches? And so to interrogate this problem, Colin Phillips and I turned to the wealth of high-resolution topographic data that's available through the USGS and open topography in the continental US, as well as the rich history of gauge recording across many rivers is maintained by the USGS. And so we carried out 54 high-resolution site investigations leveraging this high-resolution topography. And all of those sites are identified here as blue dots. And what we did is we generated a channel center line and then traced the river banks at the reach scale to create a higher resolution record of channel width with downstream distance for these individual reaches. And so when we do this, we also are looking at width discharge scaling by leveraging that gauge data. Here I'm showing it in dimensional space, where gray is an existing data compilation of many gauges, many rivers across the world, and blue are our high resolution sites. Red represents this central tendency of our data set. And so now we're in dimensional space. And so it's worth noting again that there's over an order of magnitude of variability for a given bankfull discharge. So for example, for a bankfull discharge of 100 meters cubed per second, we have widths ranging from about 10 meters to about 100 meters. And while this may not seem like a lot in terms of geologic time, in terms of engineering and infrastructure building bridges, that's a pretty big difference. And so it's important to understand whether there are attributable drivers that lead to this spread in our data sets. And so what we did with this data is first we saw that the variability in width is largely consistent across our reaches. I've now colored them just by from red to blue based on site number. And what we see, which is not surprising, is that average river width and variability in width tend to increase with increasing bankfull discharge. These are the distributions of those widths. We can then standardize our data sets. So take our width and standardize using the mean and site-specific mean and standard deviation. And when we do that with our high resolution width measurements, we see that the variability of width within all of these reaches collapses quite nicely. And so while we can explain this variability, we're now also interested in interrogating where any individual data point sits relative to our red line here. And so to do this, we're going to take our expected width, or that central tendency, and then all of our measurements, which are these blue dots, and we are going to divide our measurement by our expectation. And we're doing this rather than differencing them because we have log normal distributions. This is well described by power law scaling. So this accounts for that a little bit more clearly. So in that case, if this ratio is greater than 1, our channels are sitting above this line. They're wider than we would expect for a given discharge. If our channels are sitting below this line, they're narrower than we would expect for a given discharge. And so this ratio gives us some indication of where our channels are sitting relative to the central tendency of our data set. And so if we look at that ratio in space, we can see that we get some pockets of red where our channels are narrower than we would expect. We get some pockets of blue where our channels are wider than we would expect, but we don't see clear and consistent spatial patterns between all of our data sets here. And so what we did next is start to interrogate these gauge records to say, well, is there something different about the river flows that might be driving these offsets? And so what we did, so then what I'm plotting here, on the x-axis, I'm plotting something called bankfull intermittency. This is how often the river flow exceeds the bankfull condition. So a higher bankfull intermittency means that our river is at bankfull or above bankfull more often. On the y-axis, oh gosh, sorry, my mouse keeps wanting to jump around. And where we have lower bankfull intermittency, it means that we're more often below our bankfull condition. On the y-axis here, we're plotting those deviations in width. So that ratio of bankfull or measured bankfull over our red line, our expectation. So anything that plots below this gray line here is narrower than expected. Anything that plots above this gray line here is going to be wider than expected. And so what we see here is that those deviations in width go from narrower than expected to wider than expected with increasing bankfull intermittency. What that means is that our rivers tend to be wider when it floods for a larger fraction of the year. So rivers that exceed bankfull more often are wider than we expect. Rivers that exceed bankfull less often are narrower than we expect. And we find that this annual flood, these differences in annual flood duration may explain a 5-fold difference in channel width for rivers with the same bankfull discharge. And so this flow frequency seems to really matter. And so we can look at what then controls bankfull intermittency across all of our rivers. What I'm plotting here is that same bankfull intermittency metric on the y-axis, and then bankfull runoff, which is just the bankfull discharge divided by the drainage area for each of our sites. And you can see that as our bankfull runoff increases, our bankfull intermittency decreases. We've also calculated the aridity index for all of our points and then binned our data by that aridity index. And we can see that we're going from drier to wetter overall with that decrease in bankfull intermittency and that increase in bankfull runoff. And so just to emphasize here, this finding may represent a potential expression of those flow history dependent thresholds that I talked about manifesting in these differences in bankfull width. So rather, can we then posit that rivers where floods exceed bankfull more often ultimately have erosion threshold or have lower erosion thresholds, such that if we're more often experiencing these higher magnitude flows that are causing weakening during these flooding events, do our rivers then become wider and shallower because they become easier to erode? They need less water. They don't require as deep of water to start mobilizing sediment. Versus in rivers where floods exceed bankfull less often and are narrower than average, can we posit that these have higher erosion thresholds, such that for a larger portion of the year, they're in these low flow states where local rearrangement and stabilization of the bed occurs. Thus, to move sediment, rivers must be deeper and narrower than we would expect on average. And so this is something that we're still working on, but I think it's a really exciting demonstration in that the reach scale dependence on intermittency that we observe here is consistent with what we would expect for these flow history dependent thresholds, which I think is really exciting. It also reinforces here that there's this overarching importance of catchment hydrology and hydroclimate, both that affects sediment mobility at the grain scale, but also impacts reach scale morphology and river shape. So we have these influences across scales that are popping up here. Okay, so that was case study number 1 on river width and variable thresholds. And I want to emphasize here that in this case study, we're still only thinking about single reaches in individual rivers. And so now we want to scale up and think about whether or not we can observe spatial variations in channel width across a single catchment. And so we know that as we move downstream from our headwaters to our channel outlet, we're increasing our catchment drainage area. We're increasing our discharge. And those increases in drainage area and discharge drive downstream increases in depth, width, and velocity, or a downstream hydraulic geometry scaling that was so nicely described by Leopold and Matic in 1953. This increase in depth, width, and velocity is indicative of this increasing demand of a channel to move water as we get downstream, that channel's first job. And what we see is that in general, rivers get wider and deeper with increasing downstream distance, which is no surprise. But we also know that our alluvial river channels maintain these concave up equilibrium profiles, both because they're getting deeper as they move downstream, but also because we can vary our slope and our grain size as we're moving downstream as well. And this downstream covariation in depth, slope, and grain size typically assumes or maintains a constant threshold for motion at every point in the channel. So if we're thinking about our critical shield stress here, where our driving stresses are some function of our local depth and slope divided by our grain size, we tend to assume this constant value again around 0.05, where we have this covariation in all 3 variables to get us this nice concave profile with this very constant threshold for motion. So something that we've accepted. But those downstream increases in drainage area that require channel widening and deepening also require this reduction in channel slope. All of that's underpinned by this constant threshold for motion. Like I told you earlier, we know that the threshold for motion can vary in space. And so we're interested in looking along these catchments and say, can we extract topographic signatures of spatially variable erosion thresholds using, again, high resolution topography? And so we're borrowing here from observations that have already been well characterized in bedrock channels, where bedrock channels tend to be narrower and narrower in reaches where they are steeper. And so this is really nicely demonstrated by Finnegan et al. In 2005, in that in areas where we have accelerated uplift in bedrock rivers, reaches have to adjust to become both steeper and to become narrower to exert more erosive power on the bed such that erosion can keep pace with that accelerated uplift. And so Noah demonstrated this quite nicely and incorporated slope into downstream hydraulic geometry scaling to allow for that. And so our question is this the same in alluvial rivers? Lamb et al. Has identified that steep alluvial rivers tend to have higher erosion thresholds. So again, the river needs more erosive power in those reaches to move sediment. So we're asking or hypothesizing here that for a given drainage area, reaches that are steeper than expected should also be narrower in alluvial rivers, and that narrowing might potentially be indicative of local increases in the threshold for motion. And so this is what my student Robert Kostanek has been exploring as part of his PhD. And what I'm going to show you today are some preliminary results from that study. And so to explore this, Robert picked 5 different catchments. The Rio Amudo and the Rio Pueblo de Taos are both tributaries of the Rio Grande, and then the Eel River in California. These 3 rivers have clear nick points within them. So we have these local deviations in slope away from our nice equilibrium concave profile. We've also picked 2 lower gradient concave rivers, the Greenbrier River in West Virginia and the Merrimack River here in Missouri. So these are the long profiles that we'll be looking at. And so what Robert did along these rivers using high resolution LiDAR data set is he extracted bankfull width using what we're calling a fill and spill algorithm. This is something we built on the shoulders of Topo Toolbox, which is an incredible MATLAB-based software for topographic analysis. And so what we do is after we extract our stream network, we generate normal river cross sections every 10 meters moving downstream. At each of those cross sections, we find the thaw leg of the river, and then we measure the bank to bank distance at different elevations above that thaw leg. And then we find the point at which, or the elevation at which the bank to bank width increases very rapidly. We call this the spillover point. And so you can think about that literally as a river overtopping its banks, but we're just doing this on high resolution topography. And we've done this for all 5 of our river systems at a 10-meter resolution. And so this is what we've found. So we use that bankfull width, we extracted bankfull width using that fill and spill algorithm across those sites, generating over 50,000 cross sections. We cross-checked these measurements in the algorithm performance with hand measurements that Robert very painstakingly made to demonstrate that the algorithm is capturing what we would visually define as bankfull as well. We also calculated reach scale slopes over 500-meter moving windows. And so this is what I'm showing you here. You can see in our slopes here for our nick point channels, those nick points become very obvious to see with these very high excursions in slope. And for our lower gradient channels, we have a much smaller range of slopes that we're seeing, but we still have quite a bit of noise here. In channel width, we generally see that channel width increases downstream with these coincident decreases in slope across all of our catchments. And indeed, we can look at this data in a different way and say, on average, our steeper channels also tend to be narrower, or our lower sloping channels tend to be wider. So what I'm just showing here are box plots of our reach scale slopes and our fill and spill extracted widths for our 5 sites. And you can see that our Nick Point channels have much wider range of slopes. They have steeper slopes, and when we get to our Greenbrier and our Merrimack, very low slopes and much wider widths here. So at first glance, this seems to jive with what we would expect for our river systems. If we think about this in the context of a slope-dependent critical shield stress, what I've done is I've taken the channel slopes for slope ranges for all of these rivers and plotted that across on the Laminal 2008 plot. And what we're demonstrating here is that the range of reach scale slopes that we have across our 5 rivers spans a range of possible threshold values, which means that we might expect these differences to crop up or be manifested in our measurements of channel width as well. Okay. And so if we return to our profiles of channel slope and channel width in these catchments, again, we can see that these excursions in reach scale slope in our Nick Point channels are pretty easy to identify. And so I've highlighted them here with some gray boxes. A lot harder to identify in these low gradient reaches where we have much less variable slopes and much lower slopes. But now if we turn our attention to our profiles of channel width, if we squint, maybe we can see that in these areas where our slopes get higher, our widths also go down or maybe lower, but it's a lot more difficult to visually identify this. There's some suggestion of narrowing, but not anything that I would personally hang my hat on just by looking at these profiles. And so part of the reason for that is that we have these downstream trends that might be masking some of these deviations that we want to think about. And so for each of our rivers, we constrained downstream trends in slope and width with increasing drainage area. And so this is just an example for the Greenbrier, where we determine a slope area scaling and a width area scaling for each of our rivers. Here we can see that this river, the scaling exponents in this river of 0.5 and 0.4 generally reflect what our expected values for both slope area scaling and with discharge scaling might be. What we then do is that same exercise that we did in our first case study, where we take our data or these data points and then divide by our expectation or this line to just get our deviations. That's what I'm plotting down here. Again, values greater than 1 here are either going to be steeper than we expect or wider than we expect. Values less than 1 will be gentler than we expect or narrower than we expect. And as a reminder here, we're expecting that our deviations in slope and width should be anti-correlated. And so now I'm going to step through what these deviations look like for all 5 of our catchments. And so we're going to go slowly through each of them, but it will be quite a lot on one slide. So buckle up. Okay, so starting with the Amudo here, where we have one very clear Nick point, very clear slope excursion pops up. See that this gray line here represents that transition from gentler than average below the line to steeper than average above the line. At this point as well, we see that our deviations in width fall below that line, meaning that we're narrower than average. When we look at the deviations in this way, we can also pop up secondary feature or find secondary features that pop up that might not be as obvious when just looking at the long profile. So here again, we see this this decrease in, oh, sorry, this is slightly off. This gray box should be here. So where we get this increase in channel slope, we again see this decrease in width. Then we see this decrease in slope, and we do see that the river tends to get wider there as well. But we can see though that anti-correlation pop up quite nicely visually. We can do the same thing in the Rio Pueblo de Taos, where we have these 2 steep regions We can see those pop up quite nicely here in where our slope deviations exceed 1, and then the sustained narrowing of our channel that's coincident with that. In the eel, we also have this slope excursion where we're steeper than we expect in our headwaters. But then when we look at our widths, we don't see that same sustained width deviation that we're seeing in our other examples here. So it's a little less clear when we're looking just qualitatively at our long profiles. In our Greenbrier River that's more concave, we do see that right at the outlet, we do get this jump or this increase in slope. But strangely here, it looks like the channel might be getting wider where the slope increases rather than narrower. Again, really hard to constrain just by looking at these long profiles. And then for the Merrimack, we can see that our slope deviations are fairly symmetric and fairly noisy. And then we see something fairly consistent with our width deviations where we don't get these long sustained excursions. And so it looks like maybe our idea bears out in some of our sites, but not all of our sites, just by visual inspection. So we can look a little bit more closely at what these deviations look like for each of these channels, both the deviations in slope and the deviations in width. When we do that, what I'm plotting here are cumulative distribution functions of our slope deviations as these dark colors, and our width deviations as these lighter colors. In our nick point, what we find across all of our channels is that our slopes tend to deviate more strongly from our expected values than our channel widths. In our nick point channels, we can get really strong deviations in slope from a factor of 4.5 to a factor of 14 increase in slope relative to what we would expect. These are really big differences, but it's not super surprising when you look at our elevation profiles. In our concave channels, we see that the slope excursions are a bit more muted, and we see no slope excursions exceeding a factor of 4. In all of our settings, though, width is the less sensitive variable, and that our width deviations tend to not exceed a factor of 3. And so while our slope can be quite variable, this suggests that our channel is not only responding to those slope deviations by adjusting its width, but may be able to adjust some other things or accommodate those deviations through other adjustments like grain size, things like that. And so when we're thinking about then our channel width deviations, we want to think about them in the context of our slope deviations. Are our channels actually narrower where they are measurably steeper? And so what I'm going to show you here is that I've just started by populating these plots with the CDF. These are CDF plots of our width deviations only. You'll see that in all of these plots, we have generally symmetric deviations and that 50% of our data sets are narrower than we would expect. 50% of our data sets are wider than we would expect. When we look at all of this, like our entire data set, every slope deviation that we measure, all of our width deviations are centered around 1. Now, we're really interested in these steepest parts of the catchment. And so what we did is just extract areas where our slope deviations exceed the 95th percentile of all of our slope deviations. So these dark lines are the width deviations associated with any point on the channel where our slope deviates from for our highest magnitude slope deviations, the steepest parts of our channel where we're steeper than we would expect. What we see across all 3 of our nick point sites is that for this population, our channels are measurably narrower. So for example, the Rio Pueblo de Taos, in the steepest condition, about 90% of these cross sections are also narrower than we would expect. 80% for the Rio Amudo, and about 70% for the eel. We can also look at our gentlest catchments. So now I've added any slope deviations below the 5th percentile of all deviations, so our gentlest parts of the profile relative to what we would expect. And what we see is that here our width deviations tend to get us a little bit wider, but that response is a lot less significant than the response to these steeper slopes. And so these results are really encouraging. So what we find for our Nick point channels is that our channel widths appear to be anti-correlated with our reach scale slopes for these Nick point catchments. And these results are generally consistent with what is observed in bedrock rivers. And we posit that they might be indicative of this expression of reach scale slope dependent erosion thresholds cropping up in our measurements of bankfull width. And so it's worth noting here that these are very preliminary results. Robert only generated these plots last week, but they're extremely exciting and encouraging. But the challenge is that I've only shown you the Nick point channels. So there is a but here. If we do the same analysis on our concave channels, we see that this relationship flips. Instead, for our very steepest reaches, we actually get wider than expected rivers in both cases. And for our gentlest slopes, we get narrower than we would expect. So this was not what we were expecting, but is certainly something to try and unpack. So the question here is, what's the deal? And so this is what we're currently trying to figure out. So always open to ideas. But some of the ideas we have is that maybe there's a critical magnitude of slope deviation that we require to drive a measurable response in channel width. And so I told you that for our Nick point channels, we get much larger slope deviations up to from a factor of 4 to a factor of 15. That gets us much further in terms of changing our threshold than a factor of 4 for these very low gradient streams. So there may be a critical magnitude of slope deviation that we require here. There also may be a critical length scale of slope deviation that we need to generate or drive a measurable width response. So we're looking at Nick point catchments where we have these sustained deviations in slope in space versus our concave catchments where we have much noisier deviations in slope. And so what I'm plotting here is just a CDF plot again of the lengths of any continuous slope excursions for all of our rivers. And what you'll see is that our Rio Amudo and Rio Pueblo de Taos have very, very long slope excursions relative to the rest of our data set. Our concave channels have smaller but shorter slope excursions. And then the eel is an outlier. So I'm not quite sure what's going on with the eel. There could be some combination of these two things that's also required here to drive measurable width response. The other thing that might be true is that slope isn't really a driving variable for width response in low gradient concave channels. Maybe the width slope coupling that we observe in our Nick point channels just isn't as strong or is overwhelmed by other factors when we get to these low gradient channels. So this is very much an area of active research. So stay tuned for the update on this. But that about wraps up our second case study here. So just to conclude, I hope that I've demonstrated to you that width discharge scaling is a really robust first order observation, but there's still a lot to learn. There's this influence of variable erosion thresholds that's likely going to influence our bankfull width. And this is a rich area for future research, especially with the high resolution topography that's available now. We've also found that reach scale differences in bankfull width do vary systematically with bankfull flood intermittency. Demonstrated that local deviations in channel slope and width might also capture reach scale differences in threshold across single channels. But that there might be important magnitudes or length scales of perturbations that are required to drive measurable width adjustment in these settings. And ultimately attributing these drivers, because there are so many different ways that we can vary threshold, so many different ways that our rivers can adjust, is an outstanding challenge, but it's also an exciting one to be working on. And then just to wrap up real quick, if any of this was exciting to you, I am always looking for curious and excited PhD students. We have funded projects on developing signal to noise ratios in alluvial rivers, following up on some of this work, uplift and erosion on rocky coasts, if you like field work in California and Oregon. Funded projects on urban flooding impacts on human health using 2D, 3D data fusion and machine learning. And then damage development in bedrock rivers with experiments, X-ray tomography, UAV LiDAR, all of that stuff. So if any of this was interesting to you, please feel free to reach out to me and get in touch. All right, and with that, I'll wrap up.
Thank you, Claire. That was fantastic. I wish I could be a PhD student. It sounds like you have amazing projects going on. But this is awesome. This is all very cool. People are probably still, wrapping their heads around writing questions in the chat. And so I guess for now, if Luca or Rita have any questions, they can take the floor as well.
Yeah, I could maybe ask. Oh, Rita, you were about to go?
I
Okay.
have one, but I can do afterwards. Well, Claire, thank you so much. I do see these results very promising, especially to incorporate on drainage models. So I do think that they are really encourage the type of research that you are doing. I do have a question regarding the first part of the presentation, where you were describing some drivers for the threshold of sediment entrainment and the flood magnitude.
Yeah.
And one of the variables that you were looking at was the width, and the effects of the width. It was one of your interest variables. I was wondering if you find out any kind of tipping points related with the flood magnitude, considering the flood magnitude, but related not only with the width, but with effects of the meandering of your rivers. Is there any kind of ratio, relationship? Because we could expect different accelerations if we have a puzzle of widths and a puzzle of meanderings. How do this shape and changes in form do also assist on the flood magnitude variability?
Yeah, so that's a great question that I'll answer in two parts. So before we get to meandering, I just thinking about tipping points at an individual cross section, what we find is that it's easy to make the bed stronger, but it's pretty hard to make the bed weaker. And what we see is that similar to this idea of channel width evolving to reflect that more resistant threshold, that turnover point, let's say, when the river goes over bank, we transition from this strengthening to this weakening. So the river container evolves to reflect the maximum threshold for motion. And the challenge is that once you start eroding, then you like drop yourself back down to that strengthening condition rather than continuing to break. So it's really, really hard to push the river into breaking versus strengthening. So there is a tipping point, and this is one of the things that this signal to noise ratio is trying to get at, is how hard do you have to hit a river to break it? In meander, I think when you take meandering and secondary flow into account, it probably gets even more complicated, in that you can get this rapid widening when you're, I always mix these up, when your bank pull outpaces your bar push. And that's going to depend on sediment supply and a bunch of other stuff. It's certainly something that's important, but we just can't, even at the cross-section scale, it's really challenging to explain, but I can imagine that those differences in flow across your cross-section as you're accelerating around a meander might mean that you can break your channel a little bit more easily than in our gravel bed when we are thinking just at the cross-section scale. But that's complete conjecture.
Thank you.
Thanks, Claire. This was a really awesome talk. I'm going to take some questions from the chat, and we have a first one by Moise Baraka. A very interesting talk. Just being curious, how do variations in turbulent flow characteristics such as Reynolds stress and vorticity influence the critical shear stress needed to initiate sediment motion in riverbeds?
Great question. So vorticity, I don't know about vorticity, but that's a really interesting question because Buffington and Montgomery's 1998 compilation of the threshold for motion thinks about the particle Reynolds number. And as soon as you exceed a particle Reynolds number of about 100, they argue that you get to a fairly constant value, though what other studies have demonstrated is that you can still get a lot of variability. Thinking about flow around particles as grain scale topography changes is something that Elwyn Yeager has done a lot of work on understanding and thinking about. And so I would point you to some of her work if you want to think about changing resistance forces due to the interaction of our deformable bed at the grain scale and turbulence that's then affected by grain scale topography.
Pedro, you want to take the next one?
I can do it if you want. Okay,
Go ahead,
we
Rita.
have another question from Natalie Bergman. He says, very interesting talk, Claire. Thanks. Many of the USGS gorge streams you showed are with glacial legacy. Maybe not classic alluvial with tilt control. How does that play into the analysis?
Oh, so whether I'm going to interpret this question, if I interpret this question correctly, it's ultimately about like what the bed material and the bank material is comprised of. So in many of these places, we're cut into glacial till, and some of these places are not. That's something that we have not looked at. So in Colin's work, we focused on the hydrologic history, rather than thinking about material strength controls, because those are a bit harder to constrain. Though we didn't find any clear spatial trends associated with like areas where we have glacial legacy versus not. I think that demonstration of the map, let me go, I don't know if I want to go all the way back there, it's many slides ago, sort of show that the data are not clustered in a way that would suggest that glacier channels incised into glacial till are behaving significantly differently than channels in more arid areas or areas without glacial history. It's certainly something to look at. I mean, this is what I'd like to highlight is it's such a rich problem and there's so much data that there's always the opportunity to go look.
Thanks, Claire. We still have time, but we have another question here from Fred Phillips. He says, great seminar. When considering river-to-river comparisons, you highlighted flow intermittency and association with climate control and such as aridity index. You focused on channel and channel bed characteristics to explain patterns. However, these variables are also strongly associated with sediment delivery to the river, in parentheses, delivered sediment to water ratio. Thus, the transport characteristics of the river must adjust to the sediment delivery requirements as well. Thoughts on this?
Yeah, totally agree. Totally challenging to measure and uncouple those effects, right? And so I'll point out here that like, while we see this first order relationship, there's still quite a bit of scatter. So certainly the sediment, so we could play the game of then if we control for the hydrology, then can we unpack the sediment part? But uncoupling that might be a lot more challenging because of what would need to be measured for that. So there is much less, and we've had this idea of taking existing suspended sediment and bedload transport records and looking at those as well. But the data are much sparser than what we have for just looking at the flow history. So while I do think that is important, just to do this I think it would require a more focused site-by-site analysis. But I do agree with you that the sediment delivery part is also likely important. And what we would expect from experiments is that when you get a little more sediment delivery, we might be seeing wider than expected channels versus less sediment delivery where we can armor our bed a bit more narrower than expected. Though, again, an exciting area for future research.
Thanks, Claire. People can still write some questions if they want. I would ask a fairly obvious one, which is about the next decades ahead of us as climate is changing. And what is the time scale of adjustment that we should have in mind? Is it aridity is going to be modified across the US? Could you just tell us a bit more about that?
This is a great question, Luca. And this is like ultimately the goal of this signal to noise project that I'm just showing you some of the initial results from, in that we've tried really hard to quantify the noise that we can with the data that we have to try and figure out what signals are extractable or measurable. Our hypothesis is that which I'm sure is going to be very satisfying to everyone, is that it depends, in that if we think about this strong coupling between the threshold for motion on the bed and the shape of our container, both of those knobs can adjust to changing hydroclimate. And so if our bed can take up or can adjust quickly enough to sort of buffer the influence of changing hydrology on the width response of the river, then we might not get a lot of widening if that integration time is fast, but we might then, as a consequence of that, get more flooding. Versus if our river container is a lot more responsive, then the integration time scale of our bed to adjust, then we might get a lot of erosion, but then that drops us back down into a strengthening state and also reduces flood risk ultimately. And so our goal is to say, what are the controls on those integration times across landscapes, and which scale is sort of driving the response in the other scale. And so we're doing flume experiments, we're using numerical modeling tools to think about this, but it's a really challenging problem and is what makes projection of our river response to climate change and characterization of the sensitivity of different rivers to climate change really challenging, because there's this coupling of both the grain scale, the width scale, and also catchment scale hydrology that's come out of this. So if all of those are changing at once, it's the competition of those integration times that's going to matter. So not a satisfying answer, but hopefully an inspiring call to arms. And maybe if there are any people that want to do PhDs on this topic in the audience, they should contact me. But
thank you, Claire. I think it's a great point to end. Pedro, you want to wrap it up?
Yeah, sure. This is really great, very inspiring thoughts here, Claire. So thank you very much. And so it's a wrap we're at 11, so it's an hour, 11 for me at least. Yeah, that's it. Thank you all for coming. Thanks again, Claire, for this fantastic talk.
Yeah, thank you for the invitation.
Thank you, Claire.
All right. Do I sign off now?
Sure. Yeah.
Okay. Bye, everyone.
Need to stop recording. Bye-bye.
Bye-bye.